Hello students, today I will start a new topic, the Doppler effect, that is also associated with the wave property. You all watch the video completely. आप वीडियो को पूरा देखें, समझें और आप इसको सब्सक्राइब करें, शेयर करें. So I take the Doppler effect. Doppler's effect. Here Doppler is the name of the scientist. Until you watch the full video, you cannot understand what is given there. So, all of you watch the video completely, and if you have any kind of problem, you ask me in the comment box, or you can call me on my telephone, on my mobile number. It was discovered by Austrian physicist Christian Doppler in 1842. This effect is associated with the wave nature of sound and light. Because sound is also has the wave nature and the light also has the wave nature. So for this, both these sound and the light, this Doppler effect is also one of the important effects. Whenever there is relative motion between sound source and observer, the observer listens the frequency of sound different from the frequency of sound wave waves emitted by sound source. What we have definition? Whenever there is a relative motion between the sound source and the observer listens the frequency of the sound different from the frequency of the sound waves emitted by the sound source. So let's n equal to true frequency of sound emitted by the sound source. And n dash equal to the apparent frequency of sound listened by the observer. So if n dash is greater or equal less than the n, there is Doppler effect. And if n dash is equal to n, then no Doppler effect. No Doppler effect. It means that the apparent frequency must be more or less than the true frequency of the sound emitted by the sound source. And if it's both the frequencies are equal, then there is no Doppler effect. It means that neither the sound source nor the observer are moving, so there is no relative motion at all. No Doppler effect means no relative motion. So for Doppler effect, it is necessary that the apparent frequency must be either more or less than the true frequency. So this is what in case of the sound, and also we have that if the sound source is moving with supersonic speed, then there will be no Doppler effect. If sound source moves with supersonic speed, there will be no Doppler effect. Because the sound source moving with this speed that emits the shock waves which are very different from that of this sound that we listen in our daily life. So this kind of speed is there for this sound source, then there will be no Doppler effect at all. Now in sound, in case of sound waves, the Doppler effect is of two kinds. In sound waves, the Doppler effect is of two types. One is longitudinal Doppler effect, longitudinal Doppler effect. Now in this effect, the sound source and the observer move in a straight line, parallel or anti-parallel to each other. This effect takes place when sound source and observer move along a straight line. A straight line. And second, suppose this is now we are having the source, this is suppose now observer, then both are moving like this, or this is the sound source and it is moving in this way, this is the sound observer moving like this. This may be the case, they moving in the, along the straight line. So similarly, if we are having that, if suppose this is our sound source and it is moving with this speed, and this is now suppose observer, this is moving with this speed, etc. And so many. So there may be so many cases, but both the sound source and the observer are moving in a straight line. And second is the transverse Doppler effect. Second, transverse Doppler effect. Now what happens that here the observer moves perpendicular to the direction of the motion of sound source. This effect is observed when observer moves perpendicular to the direction of motion of the source. It means that suppose this is the sound source, here is sound source, and it is moving like this. This is, and suppose the observer, it is moving in this direction. This is now observer. The sound source is moving like this and observer is moving like this. So they have an angle between them is 90 degree. They are perpendicular to each other. In this case, what we have, we call this the transverse Doppler effect. So first we will take only the longitudinal Doppler effect and then we will have the transverse Doppler effect. First we are taking the longitudinal Doppler effect. Longitudinal Doppler effect. And now first case we take. Actually in this there may be 4 cases. Following 4 cases. Now first is only sound source is moving and observer is stationary. Second, the sound source is stationary and observer is moving. And third, when sound source and observer both are moving. And fourth, when medium is moving with the sound source and observer. So these are the 4 cases in case of longitudinal Doppler effect. So first I will take when the sound source is moving and observer is stationary. Now first case. The sound source is moving towards stationary observer. I am taking this first case. So what we have, that let n equal to true frequency of sound wave emitted by the source, and ns equal to apparent frequency. And what we have, that this is the source S, this is the observer O, and suppose both are stationary, no one is moving, and this observer is at the same position, and sound source S is moving with the speed Vs. Now this is the distance V traveled in 1 second, and this distance is Vs, so this so much is V minus Vs. Now this distance is Vs traveled in 1 second, then this will be your V minus Vs. So the frequency the true frequency n equal to v upon lambda, where lambda is the wavelength. The apparent wavelength due to motion of source, this lambda dash is equal to V minus Vs upon n. Therefore, the apparent frequency, n dash equal to V upon lambda dash. So now we put the value of this V upon V minus Vs upon n. This we put this value here. So this n dash is equal to V upon V minus Vs into n. This is the apparent frequency, and clearly n dash is greater than n. This we have taken when the sound source is moving towards the stationary observer. If suppose sound source is moving away from the stationary observer, if sound source is moving away from the stationary observer, then n dash equal to V upon V plus Vs into n. This is here, and from here you can have that this n dash is less than n. So when the sound source move away from the stationary observer, the frequency decreases. So, and when it moves towards the stationary observer, the frequency increases. So apparent frequency is more than the true frequency, and here the apparent frequency is less than the true frequency. So this is the case when the sound source is moving and observer is stationary. Now you can also can have that when this sound source crosses this observer, then you can find that when this is moving toward this one, we apply this formula, and when this goes away from this observer, then we will apply this formula. So now you can have the change in the apparent frequency. That what will be the change here. And you can see for supersonic sound source, Vs equal to V or Vs greater than V. Then in both the cases, here if we have this Vs equal to V, then n dash equal to 0. And when it is more than this one, then this n dash will be negative. So this is not possible. So n dash equal to 0 for Vs equal to V, and n dash equal to negative for Vs greater than V. It means that there will be no Doppler effect. So no Doppler effect. Hence no Doppler effect. So this is the case when we are having to this the cases that the sound source is moving and observer is stationary. Now I take the second case. The sound source is stationary and observer is moving towards the source. So what we have that this is the sound source S, this is the observer O, these are the waves, so much, and here we have this sound source as it is, but this observer is moving. This is noise, let its speed is V naught. This is now your observer O. Then this is now so much waves. See, this means what? That this observer will get the waves more than the waves emitted by the sound source because of its own speed. So, apparent frequency. Apparent frequency n dash equal to n plus number of waves received by observer due to its own speed. So this is what? N dash equal to n plus b0 upon lambda. So this n equal to b upon lambda. This is now b0 upon lambda. So this is now b plus b0 upon lambda. And this is now b plus b0 lambda equal to b upon n. This is equal to n dash. So n dash equal to b plus b0 upon b into n. So what do we have? You can see clearly from here that this n dash is more than n. Therefore, n dash is greater than n. This is the case when the observer is moving towards the stationary observer. If the observer is going away from the stationary observer, if the observer is moving away from stationary sound source, then this n dash equal to b minus b naught upon v into n. This is so much. So you can have that when this sound source is stationary and observer is moving, then we are having this formula. When it goes away from the sound source, then the frequency is less. So n dash is less than n. And here, when the observer moves towards the stationary observer, then the apparent frequency will be more than the true frequency of the sound source. So this is the second case when I have taken that the observer is moving and sound source is constant. And now third case. When sound source and observer both are moving towards each other. So what is happening that this is the sound source, this is the observer O, this is moving with the speed Vs, this is moving with the speed V0, they are moving towards each other. Then in this case you can have that because of the speed of the two, the sound source and the observer, this observer will listen more frequency than the true frequency of the sound source. So apparent frequency n dash equal to, this is now your B plus V0 upon V minus Vs into n. Because of this, its motion, this factor must be more and this factor must be less. So because of this n dash is greater than n. So n dash is greater than n. And when suppose they are moving away from each other, when both move away from each other, the apparent frequency n dash equal to V minus V naught upon V plus Vs into n. This is the one case, and so this n dash is less than n. When they move away from each other, then the apparent frequency is always less than the true frequency of the sound source. So this I have taken that when both are moving towards each other or away from each other, there are also two more cases. In this case number 3, the sound source is moving behind a moving observer. Moving observer away from the source. So now what we have, that this is the sound source, this is moving with this speed Vs, this is the observer O, this is also moving with this speed V0. So this sound source is moving with this, it is moving away from this one and this is going towards this stationary observer. Then in this case, the apparent frequency what must be there? That because of this the frequency must decrease, but because of this the frequency must increase. So apparent frequency n dash is equal to V minus V0 upon V minus Vs into n. So this factor is being less because of this n dash is increasing, but this factor is also less. So because of this n dash is decreasing. So in both the cases, when this is in this way, that this sound source is approaching to the observer when it is moving with the speed V0, then we have this apparent frequency. And now one more case that we can have. This is suppose sound source moving with this speed, and this is now observer V0. What here is what, that the sound source is going away from the observer, but observer is going towards the sound source. So because of this the frequency must increase, but because of this the frequency must decrease. What will have? The apparent frequency n dash is equal to V plus V0 upon V plus Vs into n. Because of this, the frequency must decrease, so we have taken larger factor, and because of this, the frequency must increase, so we have taken this factor also larger one. So you can have that this end as V plus V naught upon V plus Vs into N. And now we take one more case. Reflection of the, suppose we are having a railway engine and that is going towards a hill, and driver is in the engine, and what will be the apparent frequency heard by the driver? When the engine going towards the hill, then more and more sound will be reflected. So the driver will observe more sound, more frequency. But when it goes away from the hill, then the frequency will be less. The apparent frequency heard by the driver when of railway engine when the engine is going towards the hill. Hill or wall, anything may be there. Suppose this is the, and here we are having the sound source. This is the suppose engine. This is moving like this. This is moving with the speed of Vs. Then the sound wave will be reflected from this source. So we can have that this is moving with the speed of Vs. Then we can have the another sound source also here. This is now V, that the sound is moving towards the this source. So we will have what is the apparent frequency and as it will listen more frequency. So this is definitely V plus V naught upon V minus Vs into N. This will be the formula for the reflected wave. Now this Vs and V, they both are equal. Here V naught equal to Vs equal to V. I mean, let to this one, we have this. Then we can have this formula. And S equal to B plus B dash upon B minus B dash into N. This is when this is going towards the hill. This is the hill or the wall something hill. And if suppose this goes away from this one. Now the situation is like this. That this is the sound source S and it is going away from this wall. This is the hill. Then what will happen? The sound wave will be reflected by it. No doubt. This is the sound wave that will reflect. So now the apparent frequency. Apparent frequency n dash equal to V minus V dash upon V plus V dash into n. We have taken the similar case. Here when this is going towards the hill, then this is so much. When it is going away from this one, then this formula is so much. In this case, the speed of the source and that of the observer will be the same. So this is the longitudinal Doppler effect. There may be some more cases that I will discuss you on tomorrow. So you all like, share and subscribe this video. Read it completely and go through it. You all like, share and subscribe this video. Thank you very much.